Okay, let's see this. Student, let's see this table. Okay, let's check 100 hertz. Let's check 100 hertz. So with the curve A means the A wavelength, B means B wavelength, C means C wavelength. So as you can see, at frequency 100, okay, at frequency 100, A wavelength reduce 19 decibel, right? And B reduce 5.6, and C reduce a little bit. C reduce a little bit. .3, almost does not reduce it, right? However, at 1,000 equals 1 kilohertz, right? And 1,000 equals, and this dB equals 4, right? And 1,000, 1 dB equals 1 4. Okay, and they cannot reduce anything. Okay, no matter A or B or C. Okay, why? Because this is reference. Okay, this is reference. The reason at 1,000, neither A, B, nor C does nothing. Okay, because the sound level at 1 kilohertz is a reference. Because as I just told you, right, 1 dB equals 1 phone and 1,000. Let's see at 20, reduce a lot, right? This is low frequency, reduce a lot, A reduce a lot. Okay, and let's move up to high frequency. A doesn't reduce any, even increase. And C reduce more, right? Okay, let's do one question. Okay, let's do this question, but I don't have time for you to, I don't have time for you to practice, so let me just do it. Okay, let's see questions. A new type 2 sound level meters. Is tested with 2 pure tone source emit 90 decibels. Okay, the pure tones at 1,100 hertz. So let's estimate A, B, C. Okay, so let's estimate A, B, C. So first one, at 100 hertz. And what was 90, right? Was 90, right? And 100 hertz, as I just showed you. 100, A reduced 19. B reduced 5.6. C reduced 0.3. Simple as that. Okay? So this is after reductions. If we use filter at 100, so A you got 70.9, B you got 84.4, and C you got 89.9, 89.7. How about at 1,000? How about at 1,000? Okay. That's red, stone. At 1,000, A 变多少 B 变多少 C 变多少 How about at 1,000 was 90? At 1,000. How about at 1,000? 都没在听。我剥夺你坐车子的权利。Okay, you can point, you can ask one of your best friend. For example, like Soto Chen. You can ask one of your best friend. For example, like 熊同学. How about at 1,000? At 1,000, how much reduction? At 1,000, 0, right? So at 1,000 will be minus 0, minus 0, minus 0, 90, 90. Understand? At 1,000, okay, at 1,000 here. For 1,000, A, B, C will do nothing. Okay? Because the frequency is, that frequency is a reference. Everyone understand? If you understand, please raise your hand. Okay. How about at 20? EXO. How about at 20? How about at 20? You might also ask one of your best friends for help. So at 20, I just mentioned, right? Just 90 minus 50. 90 minus 24.2. 90 minus 6. Understand? Everyone? Okay? Okay, so now you understand by adjust frequency. Okay, by adjust frequency, you might change the sum, the numbers. Right? Okay, that's it. Okay, now I'm going to move on to the case study. I am going to test one question. I'm going to test one question about case study. Okay, I will give you a scenario. And I will ask you to use the knowledge you learned from this course to design a pollution control measure. Understand? Just like this. This is one example. 我会给一个那个 case study 案例，然后用你学到的知识来设计如何做一些污染的防治。Okay. So let me repeat this. In the final exam, I will ask a case study. Okay? So I want you to use, so there's no exact answer. Okay? I want you to use your knowledge that you learned in this course to design a measure. Okay, to design a measure to control any kinds of pollutions. Wasn't like noise pollution, wasn't like the hazardous pollutions. Okay, so let's see this. Okay, this is in the CTMS in our state. They use something called automatic home warning system. Okay, AHS. Starting from 1998. Okay, 1998. So this system was installed after the nearby residents repeatedly expressed the concern about disturbance created by the loud train horn. Loud train horn. Okay? So instead of the train blowing very loud, okay, when train come, right? In the past, when train come, they will put the driver will press a very loud train horn. So, oh, the train's coming, train's coming. So they want to install this so-called automatic horn warning system. Okay? So it's like this. So in the past, the driver just press the horn, right, to warn the peoples that the train's coming, So now they want to install this so-called AH system. They want to induce this AH systems. So the drivers of the car, the vehicles, and pedestrians means the who are on the streets, near the crossing, be careful. Okay, so from now on, the driver of the train will not press the horn. Okay, so let's do some comparisons. The train horns produce for noise above 70 dBA, decibel, okay? So the horn will affect the areas 265 acres, okay? However, the AHS horns just affect 37. So it has 86% reduction. Okay? So for the noise above 80 dBA, okay, the train horn affects 171 acres. But AH horns just affect 5. So it reduces 97%. Okay, for noise above 90 decibel. Okay, 90 decibel. The train horn affects 31 acres. The area of 31 acres. The AHS horn just affects less than 1 acres. So it reduces 98%. So this tells us AHS keeps the warning functions. Okay, from our surveys, right? So the AHS keep the warning function, but gradually reduces community noise. Okay, so the neighborhood will now no longer complain. Okay, so this is just a fact. This is the data, but we still need to do some survey. Okay, we still need to do some surveys from the residents. So residents. Okay, student, this is the real data. What we measures, right? Real data, scientific data. Okay, and this is more human. This is more humanities. So we take some surveys from residents. Okay, so as you can see, okay, 67% people think this is very positive. Okay, this is very positive. Okay, but still 1% think this is negative. I don't know the reason. Okay, and 6% think this is no effect. Okay, this is no effect. Okay. Okay, so I will ask you. So this is the case study about the lower noise, right? So the solutions the government installed that so-called AHS systems. Okay, AHS system. And you can also set up some regulations. The government may also illustrate, okay, set up some regulations. A regulation limiting the amount of noise. Amount of noise some vehicle can produce, right? And also some regulation require vehicle to be properly operates and maintains. Okay? However, despite the regulation, the noise level are usually only reduced 5 to 10 decibels. Okay? So regulation just doesn't work too much. Okay, you can also use some physical, for example, like barrier. Okay, for example, like barriers to produce some buffer zones, right? And you might also use some vegetations in fencing them. Okay, so this is a very good example that the noise barriers in Australia. Okay, you might also use like some kind of like the pavement, right? Like pavement. And some studies have shown that reduction noise is only a few decibels, but not enough to be significant. So it's not really working. Okay? And we know that airports also produce that of noise, right? When airplane takes off. Right? So the airport noise is something also we need to control. Something also. So we have some. Here I show some possible. The airport noise improvement. Some actions. Okay. I want you to read over, right, by yourself. Okay, and other sources of noise pollution that need to be addressed. Okay, besides the chain airports, right? Oh, constructions like now, right now, right? Construction and snowmobile, especially as a chemical engineer, how to reduce the noise, okay, produced in chemical plants. Chemical plants. Okay? That's for this slides. Okay. I would like to see this slide first. Student, I would like to take a look at the hardest west management too first. Because I got some questions. Okay, some question in the final exam regarding the hardest west measurement. Okay. Then we will go back to the noise 2 and hardest 1. Okay, I want to do this one first. Okay, I want to do this one first. Okay. Okay, everyone, please go download this PowerPoint slides. And this is teacher version, so you gotta save you some time to take notes. Okay. But next week we will try to finish this one today. But next week we will still continue to do the noise 2. Okay, the noise. How does it work? Okay, first off. Okay, the difference from the west that we talk about in chapter 10, right? In chapter 10 is. In this chapter, we are talking about west, which is Tuscan. Which is Tuscan. Okay? So you cannot just down it. Okay, you can just down it as well. Okay. So first of all, let's talk about how to minimize the west. Okay, how to minimize the west. As I mentioned previously, try to reduce from the source, right? If you reduce from the source, you will reduce the amount of the west. Okay, so the source reduction. Source reduction actually is reducing west at the beginning. At the beginning of the process. Okay? You reduce more source. You reduce more source, you will reduce more west. Okay? You reduce more source, you will reduce more west. Okay? For example, like electroplating. Electroplating, actually, this is it will produce lots of toxic substance. Okay? So in electroplating, industry can move away from cyanide-based process because cyanide is highly toxic. Cyanide is highly toxic. So you can use some other chemical instead, right? You might use some other chemical instead. So the rule of thumb is prevent waste before it is generated. Understand? Okay, so this is rule number 1, right? The source reduction. You reduce at the beginning of the process. Okay, for example, like electroplating, then you do not use cyanide-based process. Use some other process instead, right? Number 2, recycling. Which means if you can reuse or recover some useful, okay, I mean useful. Some useful waste. But if this is not useful, then forget about it. Don't waste your time to recycle it. You might spend more money. Okay? So, let's use electroplating as one example. Okay? For example, we know electroplating will produce lots of heavy metal. And we know heavy metal is toxic, right? So, maybe we can use ion exchange or reverse osmosis to recover those heavy metals. Understand? Okay, next slide. I would like to talk about TSD. So TSD stands for treatment, storage, and disposal. Treatment, storage, and disposal. Okay, treatment. So starting from treatment. Treatment means that's changing. Okay. So treatment means we know toxic chemical is dangerous, right? So toxic is dangerous. The hazard is dangerous. Let's do something, make it safer. Okay? So treatment means changing hazardous waste to make it safer. Okay, we can use that physically, chemically, and even biologically. We can change waste physically, chemically, and biologically. So try to neutralize it, make it less hazard, make it safer. So we call this treatment. So after that, you need to store your waste, right? Storage. So storage means holding it. Temporary, holding the hazardous waste. Okay, before disposal. But keep that in mind. This is temporary. This is temporary, not forever. So this is not the final solution. This is not a final solution. Okay? This is not a final solution. The last one, the disposal. Disposal means you try to placing your hazards, those toxic waste, properly and legally. Especially legally. Okay, for example, like your company, in your future, if you own a chemical company, your company make like $1 million. Okay, for example, like $1 million. but you got fined $2 million. Does it worth it? No, of course, right? So you need to trace those toxic waste properly and legally. Okay? The property means do not let it enter environment. As I told you, it might come back to you. Right? You also drink water, right? You pollute the water. This toxic, this polluted water might come back to you for revenge. Okay? So improper disposal will contaminate soil, groundwater, surface water, and even our air. So no one can avoid it. Okay, no one can avoid it. Am I okay? May I? Okay, so let's start with the treatment and disposal. Okay, let's start with treatment and disposal. Okay, so we can use the physical and chemical treatment, right? For example, like we can use precipitation, coagulation, oxidation reduction, air stripping extraction, absorption process, ion, electrodialysis, and even some biological treatment. Okay, we'll learn about this. And we can use for disposal. We can use landfill disposal, but your landfill should be spatial design. Your landfill should be spatial designs. Okay, not the landfill for the normal the city solid waste. Incineration. Okay, but keep that in mind. You need to burn the hazardous waste. Hazardous waste at high temperature. Normally more than 800 degrees Celsius. If you burn it with low temperature, for example like plastic, you burn some plastic with low temperature, you will produce even toxic chemical. It's called dioxin. Okay. Please go back and read the hazard control one. Okay. Student, I also post the hazard control one. This is very basic. Some knowledge. I want you to read over. I will go over this very quickly next Thursday. Okay. And also I post this, not this. The noise pollution. It has some calculation problem. Okay. It has some calculation problem. I will test in the exam. Okay. You might also read over it. Okay, I will go over this. I will go over this next week. Okay. Okay. Number one, precipitation and coagulations. Okay. It used mostly to remove metals, heavy metals, from the wastewater. Okay. So, if I ask in the exam, I want to remove some heavy metals, okay, from wastewater. Students say, oh, the wastewater is in environmental improvement. We are talking about the toxic. okay, the toxic heavy wastewater. You can use precipitation and coagulations to remove heavy metal from wastewater. Okay? Because the metal ion dissolve in the acidic water, okay, but they become insoluble when you adjust the pH to 8 to 10. Okay, so you can add lime. You can add lim. Okay, you can add lim. Lim is CaOH2, calcium hydroxide, lim. You can add lim to increase pH value. Okay, you can add lim to increase pH value to 8 to 10. To 8 to 10. Then those heavy metal ions will be insoluble. Understand? Everyone understand? You increase the pH value to 8 to 10. So the heavy metal becomes insoluble, and it will be easy for you to recover those heavy metals. Okay, for example, like let's use copper as an example, right? The copper will react with lim. Okay, this is lim. Calcium hydroxide, solution, lim. Okay, so then we will get this copper hydroxide precipitate. This is solid. We will get this precipitates. Okay? It will form as solid and settle out. Understand? For example, like chromiums, the same things. When you react with them, it will form solid chromium hydroxide and settle out. Understand? So by adding lim, calcium hydroxide, to increase pH value to 8 to 10, the metal becomes insoluble and becomes solid to set up, right, to precipitate. Okay, let's do these questions. I don't have enough time, so we'll do this together. Everyone take a look. The metal breaking furnace, okay? The furnace here is the company. Student, the furnace here means company. Chemical plant. The plant here is not the trees. The plant is the factory. 这个 plant 是工厂的意思啊，不是植物啊，不是树哦。OK。I was very sick yesterday. I was very sick yesterday. I took very heavy medicines. Okay, so that I can give the lectures. Okay. So actually, I feel very uncomfortable right now. Okay, let's continue. 我得那个重感冒，我吃超级重的药，才把那咳嗽压下来。我的身体也非常不舒服。Okay, let's keep going. It's installing a precipitation system to remove zinc. They plan to use pH meter to control the feeds of hydroxide solutions, okay, to increase pH, right? To the mixing tank. What pH should the controller to set and to achieve zinc influence concentration of 0.8 milligrams per liter. The KSP, guys, you know KSP, right? Is 7.68 times 10 to minus 70. Okay? So step number 1 is let's write down the KSP. If you still remember, right? From the general chemistry. All the chemistry you learned in high school. Okay. And the KSP value is 7.68 times 10 to minus 7. So step number 2, we try to convert zinc concentration. Okay, we try to convert zinc concentration. So what does question give us? They give us 0.8. But it's milligram per liter, right? So, but we need to convert into mole. So, number 1, we need to convert the milligram into gram. We need to convert this into gram, right? So, we divide it by 1 side. Number 2, we need to convert this mole. So, we will divide the atomic mass of zinc. The molar mass of zinc is 65.38. So we got 1.224 times 10 to minus 5 more per liter. Okay? So the KSP equals zinc 2 plus OH squared, right? So the zinc 2 plus equals the KSP, oh no, we're trying to find out the OH, the hydroxide squared equal KSP over zinc 2 plus. So after that, we got the hydroxide concentration 2.505 times 10 to minus 6 again. The pOH value equals minus log OH minus. So the answer will be 5.6, but not finished yet. This is pOH. So for pH, you need 14 minus 5.6. So the answer will be 8.4. Okay? So this is a question from our test book. Okay, very easy. Okay? So this is teacher's version, so I cannot skip this. Right? Okay. Everyone? So next, we can use something called wet air oxidation. Okay? This is the treatment process. This is a treatment process for liquid wax. Okay? This is famous called Zimmermann process. Zimmermann process. Zimmermann process is the thermal process used for oxidizing aqueous organic waste and waste sewage sludge. Okay, so he used oxygen at high temperature. He used oxygen at high temperature and high pressure to oxidize organic pollutant. Okay, so this means high. So high temperature, high pressures. Okay, typical condition is 175 to 325 degrees Celsius and 300 to 3000 psi. Okay, but it got some limitations. Okay, it got some limitations. It's useful. Okay, applicable means this is useful for the wet waste. Okay, or some biological treatment. Too toxic. Okay, too toxic for biodegradation, which means too toxic for biological treatment. Too toxic that you might also kill those bacteria. Okay? Okay, and you got some commercial operations, okay, in these two companies. Okay, next one is, okay, let's have a 5-minute short break. So let's have 5-minute short break from 3:10 to 3:15. Then come back, okay?